Hello and most welcome to 1284 of the series. Better write that down. Roberto, Unger and Smolin. They are pointing to the way of knowing is also the way of being. And the Newtonian paradigm is the condensed, stressed situation of many people today. It is in that way of knowing. It is causative of a lot of harm, pain, stress, loss of focus, loss of direction, because it is within the whole Newtonian paradigm there is a hidden fault that we are used to, and Roberto Unger and Smolin are both engaged in helping us to understand that. That's an enormous privilege to be blessed by the possibility for this understanding. And I realize it does good in all areas. All what I studied before, everything in my daily life, there are no exceptions, because a fault doesn't cost anything to repair. It's just benefits. You can compare it to having the handbrakes on while driving. Taking it off will not cost anything for the car. There is no exchange. I sacrifice this, sacrifice Newtonian the parallel to get into time is real. No, there's no sacrificial thing at all. It is a thought in the strictest sense, not a different way of seeing things only. It's a different way of seeing things that in itself contains a fault. So not even the supporters of the Newtonian paradigm would be happy when they discover the fault and would give up the Newtonian paradigm. I will continue where I left off, start a bit earlier to give some sort of fluency. Consider now the reverse question. Every part of nature, will every part of nature be susceptible to mathematical representation? Once again, the answer is negative. The greater the salience of time and phenomenal particularity, the more changes, and the more richly defined and individuated the natural kinds and their individual embodiments, populating the aspect of the world that we study. The more limited the use of mathematics will be. Imagine a spectrum from the domains in which we should expect mathematics to play the largest role to those in which we can expect it to play the smallest. Each place in the spectrum is defined by the marriage of a part of nature to a practice of explanation. This marriage may be dissolved from time to time. The substitution of one explanatory practice for another in the study of a certain part of nature is likely to result in a displacement of this spectrum. The easiest case for the widest application of mathematics is the tradition of physics that Galileo and Newton began. In particular, this tradition, insofar as it conforms to what in this book we call the Newtonian paradigm. The objects of this science are recurrent phenomena governed by time-reversible laws. The particularity of the explained phenomena is reduced to a minimum. They are small number of forces operating among entities whose distinctive characteristics are disregarded except with variations of mass, energy, and charges. This science finds a way to deal with change locally that leaves both the observer and the laws governing change safely outside the domain of the phenomena to be explained. Movement along a trajectory under the aegis of timeless laws is then all that is left of time. The stipulated initial conditions defining the configuration space of the phenomena to be explained are deprived of history. They wait to be promoted from stipulation to explained subject matter in some other application of the same practice. That this tradition of science should have been considered for much of the history of modern science, the gold standard of the scientific method, helps account for the overpowering authority of mathematics, not just as the language in which the laws of nature are written, but also the form of thought that is alone capable of prophesying what they are. Even the minor tradition within physics that leads from early thermodynamics and hydrodynamics to kinetic theory, and then from this theory to a revision of thermodynamic and hydrodynamic ideas, limits the sovereignty of mathematics. It does it only by invoking path-dependent and irreversible processes such as those of entropy. Yet this restraint on mathematics also has a mathematical expression, given that at the microscopic level, entropy can be defined as the logarithm of the number of accessible states. Even in this, its strongest field of application, the representation of local interactions among elementary constituents of nature. Mathematics exhibits a revealing weakness. It struggles and fails to do justice to the continuum, the aspect of nature that has to do with continuous flow and that resists division into discrete elements or betweens. Here I allude to the continuum as a feature of nature, characterized by undivided and indivisible flow, rather than as a mathematical concept. Traditionally represented as the real number line. Thus Brouwer, in his inaugural lecture at the University of Amsterdam in 1912, referred to the intuition of the linear continuum, which is not exhaustible by the interposition of new units, and which can therefore never be thought of as mere collections of units. To do justice to this pre-mathematical intuition would require, however, what mathematics is unable to give. Its origin in counting stands as an insuperable obstacle. The part of nature that displays most completely the attributes of the continuum is the passage of time. Movement in space exhibits them as well, if less starkly, given the different ways in which such movement may be understood and represented. The powerlessness of mathematics adequately to represent undivided flow is yet another aspects of its antipathy to time. It is, moreover, a limitation revealing the limitations of mathematics as a window of the central subject or matter of physics. The difficulty that mathematics experiences in faithfully representing continuous flow or movement helped provoke in the late 19th century, Dedekind's redefinition of the continuum as numerical completeness by reimagining the continuum as the completeness of the real number series. Dedekind and his successor assured the triumph of a program of discrete mathematics. The point of the Dedekind cut was to show how discrete mathematics, with its reduction of mathematical reasoning to numerical operations, could make sense of the between. In so doing, his approach did more than offer a way of thinking about numbers. It also disengaged the concept of the continuum from any conception of unpunctuated flow in time, and even of unbroken movement in space. Continuity in time and in space became close numerical successions. This was the direction that Weierstrass, having taken his cue from Cauchy, generalized and radicalized in his treatment of limits and functions. He reduced calculus to arithmetic and provided a basis for analysis free at last from geometrical metaphors. Because that basis was non-geometrical, it was also untainted by the vulgar, that is to say, by the true idea of the continuum as uninterrupted flow of movement, which can never be completely expunged from geometry. Uninterrupted movement in space is the most similar thing in the world to uninterrupted flow in time. Their shared quality of non-interruption is what the vulgar idea of the continuum connotes, and what the program of an intransigently discrete mathematics cannot brook. Thus, the insistence of this program on identifying the continuum with numerical completeness, and in particular with the real number line. It is no adequate vindication of the use of the real numbers as a proxy for the continuum to argue that the real numbers are uncountably rather than countably infinite. Discrete steps fail to turn, by virtue of being indescribably numerous, into unpunctuated flow. It may be objected that, despite its enormous influence and its claim to have shaped part of contemporary mathematical orthodoxy, this line of thinking fails to exhaust the powers of mathematics to represent uninterrupted flow in time or movement in space. There have been in the history of mathematics other points of view about this topic. Of these alternatives, the most significant was Leibniz's idea of the infinitesimal, later renewed by Abraham Robinson and others. The defenders of the orthodoxy championed by Dedekind and Weierstrass were not mistaken. However, in seeing the infinitesimal as a desperate attempt to outreach the boundaries of the mathematical imagination, it was desperate because it tried to split the difference between a world in which discrete things can be counted by discrete numbers and a world in which very small differences, such as the infinitesimals were designed to mark, fail to do justice to unbroken continuity. Excuse me. Counting separate things with separate numbers and relating configurations in space is what mathematics does easily and well, taking account of the idea or the reality of unbroken continuity is what it can try to do only by approximation and in defiance of its congenital biases and intrinsic limitations. The history of mathematics shows that these limits can be stretched. It does not suggest that they are non-existent. Consider now the opposite pole of this spectrum of openness to mathematics. Before confronting the additional problems presented by the study of humanity and of society and culture, this pole is defined by the attributes of natural history. Path dependence, the mutability of types, the co-evolution of regularities and structures, the change of change. In this realm, mathematics may remain a powerful instrument for the representation and analysis of large-scale phenomena such as population dynamics, just as it may prove indispensable to the investigation of the microscopic realm of genetic recombination. Nevertheless, the more decisive the role of a unique and irreversible history resulting from many loosely connected causal sequences, the more significant the differences among natural kinds, such as animal species, as well as among the distinctive individuals who exemplify them, and the more rapid or radical the transformation of transformation, the greater the explanatory price that mathematics must pay for its denial of time and phenomenal particularity. When we turn from natural to human history, restraints on the usefulness of mathematics in the development of causal explanation acquire a new and stronger force. All the traits of natural history that cause trouble for mathematical simplicity continue to apply. To them, however, we must now add the distinctive role and origin of the formative arrangements and assumptions of a society. These institutional and ideological structures which shape the terms of people's relations to one another and represent the most decisive element in the history of mankind, differ from natural phenomena. They are constructions or inventions. Although they are always built within the constraints of a historical circumstance, with limited practical and conceptual materials that history and imagination make available. We can know them from within, as we cannot know natural phenomena because we are their half-conscious author. By the same token, however, we can change them. The institutional and ideological structures of society do not exist univocally. They exist with greater or lesser force. With greater force to the extent that they are organized in a way that inhibits their revision. And with lesser force to the extent that they are set up in a fashion that makes it easy to challenge and change them. By inhibiting their own revision, they acquire a false appearance of naturalness, necessity, and authority. It is always in our interest to deprive them of this delusive patina, which some of the classic social theorists called reification. Our stake in the revisable character of institutional and ideological regimes is closely connected to our material interests in the development of our practical capability on the basis of an enhanced freedom to recombine people and resources in new ways. It is also bound up with our moral interests in the subversion of entrenched schemes of social division and hierarchy. Such always depend on the relative immunity to challenge of the arrangements and assumptions sustaining them. The source of such variation in the force of the structures is their origin. They do not form part of the furniture of the universe. They result from the containment or interruption of conflict over the organization of society. They are frozen politics. If by politics we understand not simply the contest over the mastery and uses of governmental power, but also the struggle over the terms of our access to one another in every area of social life. Nothing in the resources of mathematics allows it to capture the qualitative features that are central to these realities. Its instruments are of greatest use in informing the analysis of the aggregate phenomena that may be shaped by the structures of society and culture, and that have a quantitative or spatial presence in understanding and representing the structures themselves, however it may be of little use. Is not economics the most influential social science? It may be objected. A standing refutation of this claim of the limited use of mathematics in the study of society and history, does it not owe its preeminence among the social sciences to its devotion to mathematics? The tradition of economics that resulted from the marginalist revolution of the late 19th century, the economics inaugurated by Walras and his contemporaries adopted the strategy of viewing the economy as a series of interlocking markets. Its explicit aim was to develop a theory of relative prices that would be free at last from the confusions of the classical theory of value. Its implicit goal was to immunize economics against causal and normative controversy. It sought to advance this goal by transforming economics into an analytic apparatus. At the limit, a species of logic generating explanations or proposals only insofar as it is informed by causal theories and normative commitments supplied to it from the outside. The post-marginalist economics that culminated in the general equilibrium theories and in the neoclassical synthesis of the mid-20th century achieved its rigor and generality at the cost of four connected defects. The first and most important flaw is its separation of formal analysis from causal explanation. There is no basis in such an economics for causal theories of any kind. They must be imported from somewhere else. For example, from some variant of psychology, as in the contemporary practices of behavioral economics, or economics. Its empirical turn is therefore misleading, because wholly parasitic on the disciplines from which it must obtain, if not actual conjectures, then their theoretical foundation. Its mathematical devices are predictably trivial. Focused as they are on a stringently reduced understanding of its subject matter, there can be a proliferation of idle models in violation of Newton's warning not to feign hypothesis. Such a pseudoscience has trouble learning from its mistakes. It has condemned itself to eternal infancy. A second vice of this tradition of economic theory is its deficiency of institutional imagination. As soon as it moves beyond analytic purity and tautology, it is tempted to identify maximizing behavior with behavior in a market, and more momentously to identify the abstract concept of a market economy with a particular set of market institutions that happens to have become predominant in the recent history of the West. Such an economics is thus either pure and empty and potent, but compromised. A third complaint against post-marginalist economics is that, unlike the economics of Smith or of Marx, it has no substantial account of production. Its ideas about production are ideas about exchange under disguise. It views production under the lens of exchange. as implemented through a flow of funds or through a complex of contractual relations. The persistence of wage labor as the predominant form of free labor to the detriment of the superior forms of free work, self-employment and cooperation, makes it easier than it would otherwise be for economics to view production under the aspect of relative prices, and consequently of a theory of exchange. A fourth failure of this tradition of economic theory is that it amounts to a theory of competitive selection without a corresponding account of the genesis of diverse stuff on which the mechanisms of competitive selection can operate. However, the fecundity of any mechanism of competitive selection depends on the range of the material from which it selects. Such an economics resembles half of the new neo-Darwinian synthesis, the half about natural selection, unaccompanied by the half about genetic variation. The centrality of mathematics to this tradition of economic theory is inseparable from this fourfold taint, as a result of which it cannot serve as a model worthy of imitation. The very same features that make it deficient in the imagination of the structure of the economy, and therefore as well of alternative economic arrangements, are the ones that reinforce its mathematical devotions. The development of an economics free from the fourfold taint will have as one of its byproducts a reconsideration of what economics can expect from mathematics. This account of the part of the spectrum at which the pertinence of mathematics diminishes and its limitations become paramount is not yet complete. There is one other topic in nature and in science, besides natural and human history, that defies and exceeds the resources of mathematics. That topic is the universe as a whole and its history. The subject matter of cosmology. It is a subject matter that does not lend itself to the explanatory practices of the Newtonian paradigm. What may succeed as local explanation must fail for the reasons that I earlier explored as universal explanation. To make this claim is not to deny that mathematics is indispensable to the work of cosmology. The science of the universe as a whole cannot develop in isolation from the science of features or of parts of nature, reliant on mathematics. It is to affirm that mathematics meets its match and reveals the limitations intrinsic to its procedures when the phenomenon to be elucidated is the whole of the universe and of its history. The reason for this limitation is that an adequate view of the universe as a whole must emphasize the two attributes of reality to which mathematical reasoning can never give adequate expression. What for cosmology as natural science rather than just as applied mathematics stands in the place of phenomenal particularity. Is the singular existence of the universe. The universe cannot be counted. The most important fact about it is that it is what it is and not something else. What makes time real, inclusive, global, irreversible, and continuous, of decisive importance to cosmology, is that every feature of the universe, including the laws of nature, has to do with the history of the universe and forms part of this history. Cosmology must be both historical and a science. Nothing in the toolbox of mathematics shows how a historical science is to be conceived and practiced. It follows from these considerations that the effectiveness of mathematics in science is reasonable because it is relative. In the representation of the workings of nature, mathematics is good for some things and bad for others. Its power is the reverse side of its infirmities. Its power, as well as its infirmities, result from a vision of the most general and abstract features of the one real time-soaked universe from a vantage point that denies both time and phenomenal particularity. Both the reach and the limitations of mathematics increase by virtue of the process of internal development that has become the commanding force in its history. As a result of internal development, mathematics becomes ever more prodigal in the wealth of its ways of grasping how thoughts of reality may connect. By the same token, however, it loses any assurance that its ideas of connection will find application in the analysis of nature. Its growing stock of speculative conceptions never brings it any closer to overcoming its fundamental limitations. These restraints arise from its character and remain inseparable from its capabilities. The history of mathematics reconsidered right and wrong in Hilbert's program. A misreading of the history of mathematics helps inflame two contrasting sets of vanities and illusions. We may mistake mathematics for a godlike way of jumping out of mortal bodies with a limited vision and of seeing the world with the eyes of God. Alternatively, we may understand mathematics as a pre-natural faculty of invention, providentially and mysteriously useful in the scientific investigation of the world. As a further corrective to these illusions, consider another development in the history of mathematics. The one most famously exemplified by Gödel's proof and Turing's thought experiment with his machine. The most far-reaching implication of this development is the rebuff to any attempt to transform mathematics into a closed system. All of the insights of which could be attributed to the combination of agreed procedures of inference with stipulated axioms. If such an attempt were successful, mathematics would indeed resemble the workings of a machine, rather than expressing, as it does, the power of the mind to act in its other nature as an anti-machine. Gödel did more than show that arithmetic cannot be fully axiomatized. He demonstrated both that a large, consistent system, such as the propositional calculus presented by Russell and Whitehead, can make statements that cannot be proved or disproved within that system, and that a large, consistent system cannot be proved to be consistent within the system itself. The bearing of these results on the preceding argument about the nature and applicability of mathematics can best be made clear by correcting a common mistaken view of their relation to the history of 20th century mathematics. According to this view, mathematics before Gödel and Turing was on a track defined by Hilbert's ambition to reduce it to a closed system under axioms. Then Gödel and others appeared and drove mathematics out of a paradise to which it has never since been able to return. The half-truth contained in this reading of the recent history of mathematics prevents us from grasping the strange message of this history for physical science. Hilbert and many of his contemporaries and successors had, in fact, three programmatic goals rather than one alone. The frustration of the first, rather than jeopardizing the other two, has made it possible to realize them more fully than Hilbert and his party of mathematical orthodoxy could have imagined feasible. The first aim was to organize and to vindicate all of mathematics under a system of finitistic axioms and of rigidly defined methods of inference. This aspiration proved to be a dead end, despite the enormous influence it exerted thanks to Hilbert, Peano, and others, as well as to the undying example of Euclid's geometry. The second objective was to affirm the unity of mathematics against the specialities in which it threatened to fall apart, as every science had, under pressure from the conventions of the university system. The third purpose was to move the focus of attention from mathematical objects, whether spatial or numerical, to mathematical methods. Hilbert and many of his contemporaries thought that the second and third goals could not be separated from the first. They were mistaken. The first was not only based on an illusion, the illusion that Gödel and others worked to dispel. It also operated as an obstacle to the attainment of the other two. It prevented us from seeing what we can now recognize, that freed from the illusory pursuit of all-inclusive axiomatic systemization, insistence on the unity of mathematics and on the ascendancy of its methods over its objects enables us to understand and practice mathematics as a comprehensive expression of the two-sided human mind. The salvageable part of Hilbert's program helps undermine the view of mathematical reasoning as a machine, the workings and results of which follow ineluctably from the instructions that we have programmed into it. Once rid of the delusive effort to reduce mathematics to the implications of a closed set of axioms, we can reinterpret and reorient it as an instant of the mind at work simultaneously in its two registers. The first is its modular and formulaic register. Here the mind, made of discrete parts with specialized functions, works as if it were a machine. A machine is a device for reenacting the activities that we have learned how to repeat. The formula codifies the routine of repetition, which is then embodied in the machine. If the attempt fully to axiomatize mathematics had been successful, a machine is all mathematics would be, in everything save for physical embodiment. The second register of the mind is the respect in which mind work does what no machine can accomplish. The mind is surprising and transcending. It profits from the ability of the brain to alter according to the need and circumstance. The relation of structure to function. It tries out what it has not yet learned how to repeat, or therefore to reduce to formulaic expression. Surprise. It discovers what the established axioms and the canonical methods do not allow but cannot prevent, then establishes retrospectively the assumptions and procedures that enable it to make sense of them. Mathematics does not work in machine-like fashion. For all its war against time and its indifference to phenomenal particularity, it expresses the two-sided nature of the mind too fully to resemble a machine. It helps us understand a world, the one real world in which time is for real, that is also not a machine. The results of mathematics are not forever foretold in its assumptions and methods, just as the present laws of nature are not necessarily for keeps, and consequently cannot be counted on to foretell the future of the one real universe. The laws cannot be counted on to foretell the future, not because they are indeterminate, but because they are susceptible to evolution and change. A deflationary and naturalistic view of mathematics. What results is a view that recognizes the unmatched powers and the unique perspective of mathematics. It nevertheless repudiates the Pythagorean claim made on behalf of mathematics for at least 2600 years, that mathematical insight represents a shortcut to eternal truth about incorruptible objects. It sees mathematical reasoning as an inquiry into the world, the only world that there is, the world of time and fuzzy distinction, only at one step of remove. By apparent paradox that goes to the heart of what is most interesting about mathematics, its removal from time and phenomenal variation helps explain the power of mathematics to assist science. In the investigation of a world from which phenomenal variation and time can never be expunged, the denial of these intrinsic features of nature turns out to be the condition for the development in geometrical or numerical language of our most general ideas about the ways pieces of reality connect. The apparent paradox is so disconcerting in its content and so far-reaching in its implications that it constantly tempts us to make its significance. It induces a dream that mathematical insight is a way out from the limitations of the senses, even as that limitation is loosened by our scientific instruments. However, the exceptionalism of mathematics, its lack of regard for certain pervasive aspects of the world, for the sake of the enhancement of our powers to understand and to act, justifies no such privilege. On the contrary, mathematics can best or only be understood as part of our natural constitution. It can be explained in straightforward evolutionary terms and justified by the epistemological advantages that, at a price, it secures us. Such a view cuts mathematics down to size only in the sense that it presents it as a part of our embodied, action-oriented humanity. It does not, however, deny its distinctive vantage point or its irreplaceable service to natural science. On the contrary, it helps explain them. Once interpreted along these lines, the unreasonable effectiveness of mathematics is subject to a natural explanation that dissolves the appearance of unreasonableness in two convergent ways. It does so in one way by showing the cognitive and evolutionary advantages that the timeless abstractions of mathematics can have for inquiry into the temporal world. It does so in another way by suggesting that insofar as these abstractions are only obliquely connected with the phenomenal world studied by science, extending as they do by analogy and abduction what our senses and instruments allow us to see. There is no guarantee that they will be applicable in natural science. They may or may not be. There is no pre-established harmony between physical intuition or experimental discovery and mathematical representation. Many aspects of this view have precedence in the history of 20th century thinking about mathematics, as well as in the larger history of Western philosophy. Nevertheless, their significance can be fully appreciated only when they are taken in conjunction with the ideas of the singular existence of the world and of the inclusive reality of time. If time were illusory or even just emergent, mathematics could belong to the study of what lies behind emergent or illusory time. if our universe were only one of many inaccessible universes, mathematics could form part of the science of the timeless totality of these remote and hypothetical worlds. However, if all we have in this world in which we awake and nothing remains outside of time, we can give ourselves or mathematics no such excuse. What many have mistaken for an escape from ourselves turns out to be a road back into time, nature, and humanity. So that ends Roberto Unger's part of the book. Well done, everyone, for having the patience. And I was just thinking of Edward de Bono, passed away last year. Oh my God, would he have loved to read these pages, these insights into how the world is not closed and finished. I also remember his research that 90% of academia believes that you can actually come to a discovery via logic. And that's scary. There is not a single discovery that has been made by logic. Logic can be transferred to mathematics. So it's the counterpart. They are both timeless. They represent rather than be or become. They don't know become because they are timeless. So you see, the same view is also infected mathematics and physics, which is even worse. And no wonder, it was fun also that he mentions Hilbert. The Hilbert Conference in Paris is a decisive step. It pushes everything into the Platonic view. And then when the discovery, which was completely unexpected, as all discoveries, of Gödel came, it was a bit too late. It was so established. Why? Well, it's the push from physics. And in the mid-war period, it's not hard to believe that it came from all the sciences at that point, because none of them at that point contained history, possibly with the exceptions of some part of economics. Amazing, we did it. We celebrate with a view of the sun showing itself on the rose hips. Can you see? It's like a painting. Thank you very much and have a very pleasant, well, it's 12:05, afternoon.